Let's see what the question says. Mark the incorrect statement regarding the electrolytic molar conductivity. It increases as the temperature increases. So can we say temperature, if it is increasing, the conductivity, molar conductivity should increase, because we can say ions are going to travel faster. They're going to vibrate faster. The kinetic energy increases. Okay. It experiences resistance due to vibration of ions at the mean position. This was true for metallic conductors. If you increase the temperature, the resistance increases, but not for the electrolytic conductivity, right? And molar conductivity is all about the electrolytic conductors and not the metallic conductors. So this is incorrect. See, increases in concentration decreases the electrolytic molar conductivity, which most of you have given right. How come this is right? When it is saying increasing the concentration, do you understand? That means dilution is less. Lesser the dilution, decreases the electrolytic molar conductivity of both strong and weak electrolyte. This is absolutely right. If dilution is going to decrease, the molar conductivity of both strong and weak electrolyte is going to decrease. That's perfectly all right. Now, greater the polarity of the solvent, greater is the electrolytic molar conduction. So greater the polarity of the solvent. Now that's where I said the role of another constant comes into the picture. So solvent has also a constant. When we study the Debye-Huckel equation, there is a B also in that equation, which we don't study, but we just understand it through this. Greater the polarity of the solvent. Okay, think of water. Greater the electrolytic molar conduction. So think of that more is the polarity of the solvent that we are taking. That is going to help assist in the conduction. Okay, so this D is absolutely correct. B becomes the wrong answer. Obviously, it experiences resistance due to nothing of that sorts we have studied. Okay, so B becomes the answer to this question. Most of you have done it wrong. Let's see another one. Please check. This is very simple. You can answer me in the chat. For an NaCl solution, which of the following quantities go to zero as NaCl concentration goes to zero? So if concentration is going to zero, that means dilution has become infinite. Assume the solvent's contribution to conductivity has been subtracted. That means again the same thing. Solvent not playing a role is what we are considering. Absolutely correct. Absolutely brilliant. So what you have is when dilution is infinite. Please understand kappa we considered as conductance per unit volume. Now in the volume, and we also understand that more concentrated the solution, more will be the number of ions. More diluted the solution. Now diluted is it is so diluted that the ions are approximately zero and it's just water which is there, right? In a particular volume, we were understanding that as we were keep on increasing the dilution was increasing, kappa was decreasing. It will become zero when you have done infinite dilution. So B can be the best answer here. Whereas lambda m, is going to be becoming lambda not m at infinite dilution. Okay. So neither lambda equivalent nor lambda m. And of course, not G star. All right. So B becomes the answer to this question. Next. For a strong electrolyte, lambda m increases slowly with dilution and can be represented by the equation lambda m is equal to lambda naught m minus a root c. Select the incorrect statement. So be very careful. You have to select the incorrect statement. Very careful about it. Correct. So it's directly based on NCERT statement like Aditya is saying. Plot of lambda m versus root c is obtained as a straight line. We just saw y is equal to minus mx plus c. So this is a straight line with intercept lambda naught m. This is absolutely true. And slope minus a. This is also absolutely true. Value of a depends on the temperature, solvent and nature of electrolyte. Absolutely true. See, NaCl and KCl have different values. Do you understand? This is what we meant, that the same type of salts has same value of A. A depends on the type of the salt. So this is a salt which is going to give you 2 ions. And since both of them are going to give you 2 ions, so the A value will be same. C is incorrect. NaCl and MgSO4. Now you can see here we are getting 2 ions and here we are getting MgSO4. Now my magnesium 2 plus and sulfate have different value of constant A. Do you think so? They have different or they have different? When we have the Mg2 plus and SO4 2 minus, our ions are not same type. We will not call them same type. Now here when we say the same type, we also mean the charges they have. So M plus and X minus, the charges are plus and a minus. This is what we call as the same type. And here this is Na plus and Cl minus. and here Mg2 plus and SO4 2 minus. So the charges are different. This is not called same type of salts. So this is a myth buster that I chose this question for. So the NCERT statement clearly says that the same type of salt. So what is the meaning of the same type of salt? NaF, NaCl, NaBr, all of these are same type of salts. Do you understand? MgSO4, CaSO4, all of these are similar type of salts, +2, -2. So answer incorrect will be option C. D is correct. They have different? Yes, they do have different values. Okay, simple one, knowledgeable one. Some takeaways coming your way from here. Next one, please check. I have options now on the next slide. Please see. This is your 1, this is your 2, this is your 3. What do you have? You have NaCl, HCl and NH4OH. You have to plot it versus root C. You have to tell which is what, and these are the options in front of you. Please check. Let's find out this kind of a question, how to deal with this. See, the only confusion, I think everybody will rule out option D and option B, because clearly this third one is for a weak electrolyte. No doubts about that. And since this is about weak electrolyte, we have just one weak electrolyte with us, which is ammonium hydroxide. So either answer is option A or option C. Now we have to decide amongst 1 and 2. Mind you, Cl minus is the common one. So no change because of the Cl minus. Major game changer is Na plus or H plus. So mind you, H plus will show more conductance because by the virtue of it being small as compared to Na plus. So lambda m relatively for H plus is greater than lambda m for the Na plus, and that's why please see C becomes the answer to this question. One has more lambda m at the infinite dilution than the NaCl. Cl minus is common. H plus is in fact way more than Na plus, like Aditya has pointed out. So this was a good question and a great takeaway question. These kind of questions can also be corroborated with the titration questions. Okay, so this is like a molar titration, molar conductance titration that you're doing. You have apparatus, a proper apparatus to find the molar conductance. So you keep changing the dilution, you keep doing the dilution, you keep adding water, and you keep noting the lambda m, and the curves that you get will look like this. Okay, all right. Now, going ahead, let's see what else is waiting for us. Kohlrausch law of independent migration of ions is waiting for us. Let's see what it says. It is a very interesting phenomena. Kohlrausch law is a law which states that lambda naught m for a strong electrolyte can be determined by the extrapolation as variation is linear. So you can just extrapolate, and this that you're going to get, you know, is our intercept lambda naught m. Correct? We just discussed this. So here for the weak electrolyte, you can see the extrapolation doesn't work, because if you start extrapolating, you will get a line parallel to the y-axis. It is never going to meet. They are the two lines which are going to be parallel to each other. Then what do we do? How do we find out the lambda naught m? You understand the problem statement? By no means from the graph. For the strong electrolyte, extrapolation possible. For the weak electrolyte, you can clearly check extrapolation is not possible. What do we do then? Lambda naught for weak electrolyte can't be determined by extrapolation as the variation is non-linear. It is exponential curve that you're getting of lambda m versus root C. So in this case, who is going to come to our help? Well, Kohlrausch law comes to our help. So lambda naught for weak electrolyte is obtained using Kohlrausch law of independent migration of ions. So Kohlrausch examined the lambda naught m values for a number of strong electrolytes and observed certain regularities. He noted that difference in lambda naught of the electrolytes of NaX and Kx for NeX is nearly constant. Now this is interesting. That means there is a way out. That means if I'm talking about lambda naught of KCl and lambda naught of NaCl, I can write it like this: lambda naught K plus lambda naught Cl minus. Now we are doing subtraction. Minus lambda naught Na plus minus lambda naught Cl minus. This cancels out. So basically you get lambda naught K plus minus lambda naught Na plus. And the same thing was observed for KBr and NABr. So Br minus here also was subtracting, and the value of lambda naught K plus minus lambda naught Na plus that you got from taking another salt was same, right? And same was for the Ki and NaI. That means the anions which were common are not playing a role. This was the biggest hint for us that for finding out the lambda naught for weak electrolytes, we can make help of the strong electrolytes, because strong electrolytes are not a problem. You can simply extrapolate and find out the lambda naught m for them. So we can take help from them and find out the lambda naught for our weak electrolyte. So similarly, you can check the other things that were found out by Kohlrausch. So at infinite dilution or near zero concentration, when dissociation is approximately 100%, each ion makes a definite contribution. That means every ion counts. At the time of voting, every person who has a voter ID counts. When the elections are not around, everybody knows how the poor people just, when it comes to a stampede, people die just like that. So many of them. Nobody cares. The right figures, the right data is not even given to us. That's the value of a human life. But when it comes to the time of election, every card, every voter ID counts. That's the kind of the celebration which is happening here at infinite dilution, where every ion counts. Because every ion is contributing significantly. It is free from any kind of interactions now. Okay, so each ion makes a definite contribution towards molar conductivity of the electrolyte, irrespective of the nature of the other ion. Okay. Now, similarly, if I have to talk about lambda naught NaCl, how you should now start seeing them, lambda naught Na plus, lambda naught Cl minus, right? Similarly, if you have to do it for calcium chloride, lambda naught calcium 2 plus 2 lambda naught Cl minus, right? This is how we can write at infinite dilution. Similarly, if we have aluminium sulfate, we can say 2 lambda naught aluminium 3 plus 3 lambda naught SO4 2 minus. So basically, every individual ions in the stoichiometry as it is plays a role. You got that? Okay. Now we can say for any such AXBY kind of a solution, we can simply write lambda naught as the stoichiometry as it is, the lambda naught of that particular ion at infinite dilution, stoichiometry as it is, lambda naught of the ion as it is. Okay, so X and Y are the number of cations and anions respectively after dissociation of the electrolyte. Now, here is a question waiting for you. Can you try attempting this question? Wow, this turns out to be a Bumrah ball. 36% of you gave option B as the answer. Okay, and 27% of you said option A. 36% said option B. 9% went with option C and 27% with option D. Let's read. This is interesting. It's getting interesting and interesting. Infinite dilution, each ion makes definite contribution to conductance of an electrolyte. Whatever be the nature of the other ion of the electrolyte, that is not how it works. Hello. Kohlrausch law is applicable for what kind? NaCl I wrote, CH3COOH I wrote. Okay, so you can write acetic acid as lambda naught CH3CO minus and lambda naught H plus. A statement that we should hold our thoughts on. Okay, let's read option B. Each ion makes definite contribution to equivalent conductance of an electrolyte, whatever be the nature of the other ion of the electrolyte. So, to the conductance, it says, to the equivalent conductance, it says, finite dilution, each ion. So, this is incorrect. Finite dilution is not happening for Kohlrausch. It has to be infinite dilution. C cannot be your answer. Infinite dilution of each ion makes definite contribution to molar conductance. So, one is conductance, which is G. One is equivalent conductance, which is lambda equivalent. One is molar conductance, which is lambda M. So what was it? Lambda not equivalent, did I ever write? Lambda not, or G is ever what I write? G naught is what I wrote. I said lambda not M. So these all are the lambda not M's, okay? They are not any lambda, they are molar conductance. So if M was here, that means M is here, M is here. If we are talking about the other one, M is here, that means M is here, M is here. If M is here, that means M is here and M is here. So what becomes the right answer to this very interesting question, which had all the options very similar? It's just that one was saying that we had lambda M, we had G, or we had lambda equivalent. What should be the right answer? I think you got it. Why it went wrong? Huh? So please, my lord, it was a great question, a great tester to your reading skills and your inference skills. And D becomes the answer to this question, which only 27% of you gave right. Most of you went with the equivalent conductance, which we never talked about. Okay? But ma'am, it says depending on the other ion. See, depending on the nature of the electrolyte, nature of the other ion of the electrolyte doesn't matter, of course. Depending on the nature of the other electrolyte, how will it make a difference to you? Do you understand? If I have a strong electrolyte, the lambda naught M will come very quickly from the data itself. But if I have a weak electrolyte, then also I can have a proper infinite dilution for that, and that can be derived actually from the stronger one. So depending on weak and strong, it should be different, and that's what it says, and that's what our Kohlrausch law also says, right? So this is as per your definition that you need to know. So that infinite dilution, each ion makes definite contribution to molar conductance of an electrolyte depending on the nature of the other ion of the electrolyte. This is the second part of it is not disputable. The first part is a decider here. Okay, all cool? Interesting one. Makes you think. Now we're going to make use of the application. The application number 1 coming your way to calculate the limiting molar conductivity, lambda naught m for weak electrolytes, the way I was just talking about. So we can make use of the Kohlrausch law and apply it for acetic acid or ammonium hydroxide. How can we do that? From the individual values of the lambda m ions. For example, if you have to find out the lambda naught of acetic acid, we know we will be having at infinite dilution acetate ion and H plus ion, correct? So we can say lambda naught CH3 COO minus lambda naught H plus, and all of these, mind you, now I'm not writing M and M because M is written here, meaning that molar conductivity is what we're talking about. So this we can write, and this can be found out. The values of lambda naught M values of the strong electrolyte can be graphically obtained, but we know that for weak electrolyte they can't be graphically obtained, but we can take help of the strong electrolytes. Let's see how. Check. This is a question waiting for you. How will you take help of the strong electrolyte to find out the lambda m of the strong electrolyte? Before you attempt, let me give you an insight of this one. That, for example, here for acetic acid, this is what we had to find out. So how about we can take lambda naught HCl plus lambda naught CH3 COO minus Na plus, sodium salt of acetate ion, minus lambda naught of NaCl. Do you understand? This will give me the lambda naught CH3COOH. Now, the moment you're taking a salt, this becomes a strong electrolyte. This is a strong electrolyte any which ways. HCl is a strong electrolyte. So you can see that what will be left is CH3COOH. NaCl will cancel out and you can get the answer. Similar lines you have to think for this one now. I'm just correcting the orientation. Give me a second and you can start solving it. Nation wants to know why option C. It was going so well. 100% right answers were on the way. So let's check. You can see ammonium hydroxide, lambda naught NH4OH plus lambda naught NH4Cl minus lambda naught HCl. What will that give you? It will never give you NH4OH. That's what we want. So C cannot be your answer at any cost. But if I take NH4Cl and add to it NaOH and subtract NaCl, Na plus gone, Cl minus gone, what is left is ammonium hydroxide. That's what we needed. D becomes the answer to this question. Okay, so these kind of questions were direct. You can be given a value and be asked the answer for that. For example, this kind of a question, please go get started. So it was direct values that you had to take into account. So you have to subtract NaCl, you had to add HCl plus CH3COONA. This will give you CH3COOH if you subtract NaCl from it. So lambda naught of this plus lambda naught of this minus lambda naught of this. Let's put in the values. So lambda naught of HCl, the only mistake that can go here is if you're not putting the values respectively, like you have to be careful that the second value given to you is of HCl and you have to add to it CH3COONA. The third value given to you, 91, is the value of your CH3COON. Let's do the addition. 6, 9, 10, 11, 4, 5, 516.9. Now you have to subtract NaCl value to it. So minus 126.4. 4, 5, 6, 7, 8, 9. 5 here, 0 here, 4 here. So 9 here. 390 with a plus becomes your answer, 390.5. So D becomes the answer to this question. All that you had to do. The questions we have been solving now. All you had to do is substitute the values. So if you've done that properly, this question cannot go wrong at any cost. All right, easy peasy. Let's move ahead. Let's see if anything else is waiting for us. Another application to determine the degree of dissociation alpha and dissociation constant Ka. Now, do not forget, for example, if I'm talking about acetic acid, this is again your equilibrium chapter, the chapter you love the most. So from the equilibrium chapter, you learned that you would get these ions in equilibrium. So if you're starting with concentration at T equal to 0 as 1, after sometimes it will be 1 minus alpha, this will be alpha, this will be alpha. So if this is your moles, okay, and if we have to deal with the concentrations, so you know that we will be taking C And we are starting with the initial concentration also of C, right? So this is at time T equal to T equilibrium. So what will be our Ka? Concentration of acetate ion, which is C alpha. Concentration of H plus at equilibrium, which is C alpha, divided by concentration of acetic acid at equilibrium, which is C 1 minus alpha. So C, one of the C's cancel out. Now alpha, because it is so less than 1, right, that we can take denominator approximately 1. So Ka is going to be equal to C alpha square. Do not forget this. This might be of help. Do not forget this. We're going to make use of this, what you learned in chemical equilibrium here. So, and find out Ka if you know alpha. Now, the question is, how do we find out alpha? So, that's the question that we have to decode. We can make help of the lambda naught that we are finding out. So, please check. This is what I just discussed with you for a weak electrolyte. So, you know that in order to find out alpha, all you can do is lambda m will be proportional to the degree of ionization. At concentration, some concentration C1, whatever is the concentration that we will have some alpha associated to it, right? And when we are taking the concentration 2 equal to 0, that means we are doing infinite dilution, you know, alpha 2. So this will be alpha 1. This will be some value, but this will be equal to 1 because if this is infinite dilution, C2, then alpha 2 becomes 1. So we can say alpha becomes equal to lambda C by lambda naught m at concentration C divided by lambda naught m. This expression will give us alpha, and if we know alpha, we can find out Ka also. That's how simple things are. So you can see this is what you already know. We are going to substitute everything from here. So this is what we get. Alpha, I just explained you how we got C alpha square by 1 by taking some approximations here, correct? Yeah, so this is what you have, and you can put your value so you can see what answer you get. Ka value you can directly get from here. This again you can substitute as 1. Alpha you are substituting as lambda m by lambda naught m. So C lambda m by lambda naught m whole square will give you the Ka value. So this is what is a great application. Let's try a question on this and see whether you've understood this or not. There you go. 52% of you give the right answer. Not a good score. So specific conductance is given to us as 0.01 molar or of a 0.01 molar of a weak monobasic solution as this. So lambda m is going to be kappa into 1000 by m. Let's just substitute the value. So 0.20 into 10 to the power minus 3, it's in centimeter inverse. So 10 to the power 3 we have to multiply with, divided by the molarity given to us is 10 to the power minus 2. This is your lambda m. And this can go above. This cancels out. So you get lambda m equal to 0.2 into 10 to the power plus 2, isn't it? This goes above, it becomes 10 to the power plus 2, correct? Now, we have lambda naught given to us as 400. So you know that lambda m by lambda naught, this is your alpha, and if you multiply it by C, you will get, and the square of this, you will get Ka for a weak electrolyte like Ha. So you can just substitute the values. 10 to the power minus 2 into lambda m we just got as 0.2 into 10 to the power 2 divided by lambda naught, which is 400. Let's get rid of this decimal. So we get square of this, 1 here, 2000 here, right? 2 zeros were here. So let's just get rid of 2 zeros from here. So we will get 10 to the power minus 2 divided by 1 by 20 to the power 2. So what do we get? 10 to the power minus 2 into 1 by 2 into 1 by 2 is 1 by 4. 1 by 10 into 1 by 10 is 100. This 1 by 4 is 0.25. 0.25 into 10 to the power, this goes up minus 4. So do we have 0.25? No, we have answer in 2.5. Let's take one decimal to the right hand side and multiply with 10 to the power minus 1 so that we get our answer as 2.5 into 10 to the power. So I can just put a decimal. So you can see I will get 0.25, right? So answer is coming out to be option A. This is what we got. Everybody, A was the answer, right? So well, with this, actually this chapter, the numericals of this chapter comes to a completion. The Kohlrausch law of infinite dilution, do expect a question from here. If the highest degree of questions has to come, it will come from the application of the Kohlrausch law in the form of alpha. If simple questions are supposed to come, then it will just make sure that you just rearrange your strong electrolytes in such a way that you get the lambda not at lambda not for a weak electrolyte.